Hi students, now we are going to discuss about nature of carbon X bond in haloalkane. Carbon X bond. And then carbon is obtained from the hydrocarbon. X is obtained from the halogen. Yesterday we were discuss about in then what is meaning of haloalkane, halorine. In then what are the classification of haloalkane, halorine. What are the hybridization of haloalkane, halorine. In the nomenclature of haloalkane, halorine. But now we are going to discuss about nature of carbon X bond in haloalkane. For example, methyl chloride CH3 bond Cl is a methyl chloride. Ethyl chloride CH3 CH2 bond Cl, ethyl chloride. In methyl chloride, ethyl chloride, in the halogen of Cl, what is a halogen? 17th group elements is called halogens. Fluorine, in the chlorine, bromine, in the iodine, astatine, fluorine, chlorine, bromine, iodine, astatine is a halogen. That halogen directly bond with the alkyl carbon known as haloalkane. Alkyl carbon known as haloalkane. What is the nature of bond in between carbon and halogen? Carbon and halogens. In the carbon bond halogen is a highly polar nature because of electronegativity difference between carbon halogen higher. Electronegativity. What is the meaning of electronegativity? Or 5 type of properties are there. The properties it is used to indicate the characteristic of a periodic table. One is atomic radii, ionic radii, ionization energy, electron affinity. The last one is electronegativity. What is the meaning of electronegativity? Relative tendency of an atom accept shared pair of electron itself. Accept the shared pair of electron towards itself known as electronegativity. Electronegativity difference in between carbon halogen, carbon fluorine, carbon fluorine, carbon chlorine, carbon bromine, carbon iodine in haloalkane, or then C is equal to CH3 means then CH3CF, CH3Cl, CH3Br, CH3I, CH3I methyl iodide, methyl bromide, methyl chloride, methyl fluoride. Those compounds which contain carbon halogen bond, carbon fluorine bond, carbon chlorine bond, carbon bromine bond, carbon iodine bonds are highly polar nature because of electronegativity difference between carbon halogen is higher. So electronegativity difference increases in between the carbon halogen. That's why carbon halogen bond break. Carbon halogen bond break. Small amount of energy required to break the carbon halogen bond. That bond contains totally how many electrons? 2 electrons. Both the electrons move towards the highly electronegative halogen side. That bond break, both lone pair of electrons move towards the fluorine side, chlorine side, bromine side, iodine side. So iodine it become a negative charge, bromine become a negative charge, chlorine become a negative charge, fluorine also it become a negative charge, carbon it become a positive charge because of it is an electron deficient species. Why? Electronegativity difference between carbon halogen bond increases. That's why the bond formed between the carbon X bond is a break. The bond contains totally how many electrons? 2 electrons. Both the electrons move towards the highly electronegative carbon side. That's why carbon it occurs partially positive charge. Halogen occurs partially negative charge. In haloalkane compound contain carbon occurs the partial positive charge, halogen occurs the partially negative charge. Partially positive charge and partially negative charge. Positive and negative charge. The next one, what is the hybridization of carbon and the X bond? In haloalkane, C bond hydrogen, hydrogen, hydrogen bond X. That carbon directly bond with X. Another one, that carbon bond with 3 hydrogen atoms are there. What is atomic number of carbon? 6. Electron configuration 1s2, 2s2, 2p2. Valence cell is 2s2, 2p2. Valence cell 2s of cell. Another one, 2p subcell. 2p subcell. 2s subcell contain total how many electron? 2 electron. It means called one lone pair of electron. 2p subcell contain how many electron? 2 electrons are there. One vacant orbitals are there. Ground state electron configuration of carbon is 1s2, 2s2, 2p2. Ground state electron configuration of carbon is 1s2, 2s2, 2p2. In exit state electron configuration of carbon is 1 electron transfer from S subcell to P subcell. Because of P subcell contain 1 unpaired electrons are there. So 1 electron transfer from S subcell to P subcell. That's why 2s subcell contain 1 electron. In the P subcell contain 3 electron. All orbitals are half-filled. In the 1 s orbital, the 3 p orbital hybridized to form of sp3 hybridization. Totally, how many sp3 hybridized orbital present in a carbon in halokane? 1, 2, 3, 4. It is a sp3 hybridized orbital, sp3 hybridized orbital, sp3 hybridized orbital. It is also sp3 hybridized orbital. So, totally 4 sp3 hybridized orbitals are there in carbon in haloalkanes. Among the 4 sp3 hybridized orbital, 3 sp3 hybridized orbital utilized in the formation of 3 hydrogen atom of 1s orbital means to form of methyl halide. 3 sp3 hybridized orbital directly bonded with 1 hydrogen to another carbon not secondary alkyl halide. 3 sp3 hybridized orbital bonded with 3 carbon atom no hydrogen and tertiary halides. Here, then 3 sp3 hybridized orbital 1, 2, 3. 3 sp3 hybridized orbital utilized in the formation of hybridized with 1s orbital of hydrogen atom. 1s orbital of hydrogen atom. Remaining 1 sp3 hybridized orbitals are there. That 1 sp3 hybridized orbital partially overlap with partial p orbital of halogen because of all halogen outermost cell electron configuration ns2 np5. ns2 np5. Ns subcell contain how many electron? 2 electron. Np subcell contain how many orientation? 3 orientation. How many electrons are there? 5 electron. According to half-half principle, Pauli exclusion principle, Hunt's rule, in the p orbital also accommodate totally 5 electron. In then how many lone pair of electrons? 1, 2, 3 lone pair of electrons. 1 unpaired electrons are there. That 1 unpaired electron utilize the formation of what? Then overlap with hybridized with in the last sp3 hybridized orbital of carbon atom. So among the 4 hybridized orbital, 1 hybridized sp3 hybridized orbital of carbon atom utilize the formation of covalent bond with in the what? Unpaired electron of halogen atoms. Okay. Then top to bottom size increases because of atomic number increases. Atomic number increases. Fluorine, chlorine, bromine, iodine. Down the group in 17th group elements of halogen, down the group, or as we move from top to bottom, size of the halogen increases. Size of the halogen increases. Fluorine, chlorine, bromine, iodine. Fluorine, chlorine, bromine, iodine. Carbon, in then carbon, you fluorine. Then carbon, in then chlorine. Carbon, then bromine. Carbon, then iodine. In the carbon fluorine bonds, this is carbon fluorine bond, this is carbon bromine bond, this is carbon iodine bonds. It is a carbon iodine bond, it is a carbon bromine bond, it is a carbon fluorine bond, it is this bond distance is carbon fluorine bond. So as we move down the group, size of the halogen increases, bond length also increases, bond length. Carbon, fluorine, shorter bond length, then chlorine, then bromine, then iodine. So down the group, the bond length increases. Bond length increases means a bond strength. Bond strength decreases. Bond dissociation energy also decreases. So as we move from down the group, size of the orbital increases in halogen atom. Bond length increases. Bond strength decreases. Bond dissociation energy also decreases. That's why small amount of energy required to easily break the hydrogen iodine bond, then hydrogen bromine bond, then hydrogen chlorine bond, then hydrogen fluorine bond. Carbon fluorine bonds are stronger bond than what? Is that strong? Carbon fluorine bond is a stronger bond than carbon chlorine bond, carbon bromine bond, then carbon iodine bond. So carbon iodine bond is a weaker bond because of size increases, bond length decreases, bond dissociation energy decreases. That's why it is a small amount of energy required. That carbon iodine bonds is easily break, so easily removed as a high halide ions of I minus. Okay, so down the group, size increases, bond length increases, bond strength decreases, bond dissociation energy decreases, polarity also increases as you move from down the group. As you move from down the group, polarity of carbon iodine higher. It is a what? It's a nature of carbon X bond in hollow alkane. Next one, we are going to discuss about preparation of alkyl halides. Preparation of alkyl halide. In the first one, from alcohol. The alkyl halide can be prepared from alcohol. Another one, the alkyl halide can be prepared from alkene. Then alkane. Then halogen exchange reaction. Exchange halogen reactions. What is the exchange halogen reactions? Finkelstein reaction, Schwarz reaction, Hunt's-Ricker reactions. It is a exchange halogen reaction. Alkane, nucleophilic substitution reaction takes place. Alkene, Markovnikov addition reaction takes place. From alcohol, it means called a Lugas test. It is also one of the nucleophilic substitution reaction. Yes, first one, from alcohol. In the alkyl halide or haloalkane, can be prepared from the first one is alcohol. Ethyl alcohol, CH3, CH2OH, ethyl alcohol. Isopropyl alcohol, CH3, CH, then CH3 bond OH, isopropyl alcohol. Then tertiary butyl alcohol, CH3C, then CH3, CH3 bond OH, tertiary butyl alcohol. In the primary alcohol, secondary alcohol, tertiary alcohol react with the concentrated hydrochloric acid and anhydrous zinc chloride. Alcohol can be converted into alkyl halide. By using concentrated hydrochloric acid. Another one, thionyl chloride, SOCl2, sulfonyl chloride, thionyl chloride. The next one, phosphorus halides, phosphorus pentachloride, phosphorus trichloride. So hydrogen chloride in presence of in the anhydrous zinc chloride, phosphorus pentachloride and phosphorus trichloride. In then what? Thionyl chloride, SOCl2, sulfonyl chloride is used to convert the OH group to Cl. Okay. In the hydrochloric acid and anhydrous zinc chloride. In the OH group replaced by Cl, CH2Cl plus H2O removed. Then OH group replaced by CH3CH and then CH3Cl plus H2O. In tertiary butyl alcohol contain OH group replaced by in the what? CH3C, CH3 one Cl plus H2O. Here also in the HCl and anhydrous zinc chloride, HCl and anhydrous zinc chloride, hydrochloric acid and anhydrous zinc chloride. In this reaction, distinguish between the primary, secondary, tertiary alcohols because of primary alcohol react with the concentrated hydrochloric acid and anhydrous zinc chloride to form of a primary alkyl halide. No durability. What is the meaning of durability? Precipitate. Precipitate formed between the acid base. We have already learned. In then what? Acetic acid react with the sodium attraction to form of sodium acetate as a precipitate. Let nitrate react with the potassium iodide to form of a in then what? Lead iodide as a precipitate. Silver nitrate react with the sodium sulfate to form of silver sulfate and sodium chloride as a precipitate. So what is meaning of a precipitation reaction, ion exchange reaction, nullification process, neutralization reaction, all methods are the same. What is meaning of a precipitation reaction means two unknown solution mixed with each other to form of solid substance of precipitate known as a precipitation reaction. Here, turbidity also one of the precipitate can be obtained from primary alcohol, secondary alcohol, tertiary alcohol, react with concentrated hydrochloric acid and anhydrous zinc chloride. This mixture of concentrated hydrochloric acid and anhydrous zinc chlorides are Lucas reagent. Lucas reagent. In this Lucas reagent, it is used to convert the OH group to Cl. Alkyl alcohol can be converted into alkyl halides. Alkyl alcohol can be converted into alkyl halides. In primary alkyl alcohol can be converted to primary alkyl halide. No turbidity appears. Is only on heating. The turbidity appears only on heating. Secondary alkyl alcohol can be converted into secondary alkyl halide. The turbidity appears after 5 to 10 minutes. After 5 to 10 minutes. Here tertiary butyl alcohol can be converted into tertiary butyl chloride. Turbidity immediately appears. Turbidity immediately appears. So in this reaction, distinguish between the primary, secondary, tertiary alcohol. Because of in the mixture of alcohol in the what treated with concentrated hydrochloric acid, concentrated anhydrous zinc chloride means to form of alkyl halides, primary alkyl halide, secondary alkyl halide, tertiary alkyl halide. In tertiary alkyl halide, turbidity appears immediately. Secondary alkyl halide, turbidity appears after 5 to 10 minutes. Primary alkyl halide, no turbidity appears only on heating. In this reaction is a distinguish between primary, secondary, tertiary alcohols. Another one, in the tertiary butyl alcohol, CH3 bond C, CH3, inga bond CH3, inga bond OH. Tertiary butyl alcohol is treated with concentrated hydroiodic acid in presence of potassium iodide and orthophosphoric acid H3PO4 orthophosphoric acid. Here OH group replaced by iodine CH3 C, CH3, and then CH3 bond I plus H2O removed. Here also OH group replaced by iodine. OH group replaced by iodine. In this reaction, alcohol can be converted to alkyl halide by treated with hydrochloric acid. Don't forget, by treated with hydrochloric acids. It is one of the important method. It is used to convert the alcohol can be converted to alkyl halides. The next one, in this process, in the order of reactivity of alkyl alcohol with halogen, hydrohalogen acids, HIs. Hydroiodic acid is more reactive, then the hydrobromic acid HBr, then the hydrochloric acid HCl, then the hydrofluoric acids. Because of already I told to you, in the top to bottom size of the orbital, the size of the halogen increases, top to bottom bond length increases, bond strength decreases, bond dissociation energy decreases. That's why in the what stability of the then carbon halogen bond top to bottom decreases. Top to bottom decreases. That's why hydrogen halide, that means called hydrogen iodide, is a more reactive, then the hydrogen bromide, then the hydrogen chloride, then the hydrogen fluoride. Among the hydrohalo acids, hydroiodic acid is the strongest acid, then the hydrogen bromic acid, hydrochloric acid, hydrofluoric acids. So order of reactivity of halo acids, hydrogen halo acids, hydrofluoric acid, chloric acid, bromic acid, iodic acid with alkyl alcohol means hydroiodic acid greater than, hydrobromic acid greater than, hydrochloric acid greater than, hydrofluoric acid. Next one, in the order of alkyl alcohol with in the what hydrohalic acid, that means called hydroiodic acid, hydrobromic acid, hydrochloric acid, hydrofluoric acid is tertiary alcohol is greater than, secondary alcohol greater than primary alcohol. It is the order of reactivity of hydrohalo acids with alcohol. It is the order of reactivity of alcohol with hydrohalo acids or hydrohalogen acids. Okay. In the next one, alcohol can be converted into alkyl halide with phosphorus halides. Phosphorus halides. For example, ethyl alcohol, phosphorus pentachloride and phosphorus trichloride PCl3. In the ethyl alcohol CH3 CH2OH, ethyl alcohol react with phosphorus pentachloride PCl5, phosphorus pentachloride. Carbon oxygen bond break, oxygen hydrogen bond also break. In the PCl5 dissociate form of Cl, here Cl, here PCl3. So CH3, CH2Cl, POCl3, HCl. So gives CH3, CH2Cl plus POCl3 plus HCl, hydrochloric acid removed. This method, general method to preparation of alkyl alcohol can be converted to alkyl halide by deed with phosphorus pentachloride. Next one, in the same alcohol, CH3, CH2OH react with phosphorus trichloride means. By using of phosphorus trichloride, we require in the 3 moles of ethyl alcohol to form of 3 moles of ethyl halide, ethyl chloride, CH2Cl, ethyl chloride plus phosphorus acid H3PO3 removed. In phosphorus pentachloride, general method is easily dissociated to form of alkyl halide, phosphorus oxychloride and HCl removed. But by using of phosphorus trichloride, ethyl alcohol can be converted to ethyl chloride and phosphorus acid H3PO3 are formed. It is one method. Another one, by using of SOCl2, sulfonyl chloride. Sulfonyl chloride. The same N-propyl alcohol or ethyl alcohol CH3, CH2Cl, CH2OH, ethyl alcohol react with sulfonyl chloride SOCl2 or thionyl chloride. The bond is a break. In how many chlorines are there in thionyl chloride or sulfonyl chloride? 2 chlorine. Here 1 chlorine, here 1 chlorine. Remaining SO, CH3, CH2Cl, SOO, SO2, HCl. So CH3, CH2Cl plus SOCl2 plus hydrochloric acids, ethyl chloride, thionyl chloride, SO2, not SOCl2, SO2 sulfur dioxide plus hydrochloric acid removed. CH3, CH2Cl, ethyl chloride, SOO, SO2 plus HCl removed. So ethyl alcohol can be converted to ethyl chloride by using of thionyl chloride. It is one of the method to convert the alcohol to alkyl halides. This reaction, otherwise called Darcy reaction, important name reaction, Darcy's reactions. So in this method, all are conversion of alcohol to alkyl halide. First one, Lucas test, concentrated hydrochloric acid, then anhydrous zinc chloride. Another one by using of phosphorus pentachloride, phosphorus trichloride. The next one, thionyl chloride, SOCl2, in the process otherwise called Darcy reactions. Darcy reaction. Next one, from alkene. In the alkene can be converted into alkyl halide is the example of Markovnikov addition reaction. It's an important method. Markovnikov addition reactions. What is the Markovnikov rule? 2 types of rules are there in addition reaction. One is a Markovnikov addition, another is anti-Markovnikov additions. What is a Markovnikov addition? Negative part of the addendum attach itself carbon giving less number of hydrogen in olefin. Addition reaction all takes place in an unsaturated compound with multiple bonds. In olefin, unsymmetric olefin, alkene, unsymmetric olefin, CH3, CH double bond, CH2. It is unsymmetric alkene because of totally 3 carbons are there. One side methyl groups are there, another side 2 hydrogen groups are there. That's why it is unsymmetric alkene. That unsymmetric alkene react with in the what? Hydrochloric acid or hydrobromic acid. Hydrochloric acid or hydrobromic acid. Hydrochloric acid, hydrobromic acid dissociated to form of H plus and Br minus because of electronegativity difference between the hydrogen bromine is higher. That's why hydrogen bromine bond is separate. The bond contains 2 electrons. Both the electrons move towards the highly electronegative bromine side. So hydrogen always occurs the partial positive charge, bromine occurs the partial negative charge. So hydrobromic acid, not only hydrobromic acid, hydrofluoric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid, dissociate form of H plus and Br minus. Br minus is a negative part of the addendum. The Br minus is negative part of the addendum. Note the point, negative part of the addendum. In the negative, according to Markovnikov rule, negative part of the addendum attach itself carbon having less number of hydrogen atom, carbon occurring less number of hydrogen atom, carbon bearing less number of hydrogen atom. Total in this compound, totally how many carbons are there? 3 carbon. One is a CH3 carbon, CH carbon, then CH2 carbon. CH3 carbon contain totally how many hydrogen? 3 hydrogen. CH carbon contain totally how many hydrogen? 1 hydrogen. CH2 carbon contain totally how many hydrogen? 2 hydrogen. Among the carbon, which carbon has a less number of hydrogen? Center carbon. Because of that carbon bonded with only one hydrogen atoms are there. That's why in the negative part of the addendum attach itself carbon heavy less number of hydrogen atom of center carbon according to Markovnikov rule. According to Markovnikov rule. The negative part of the addendum attach itself carbon heavy less number of hydrogen. Next one, in the hydrogen attached to another carbon. So to form of CH3, CH, and then Br, bond CH3. In this reaction, Markovnikov addition reaction. Or alkene can be converted into alkyl halides, alkyl halide. Next one, anti-Markovnikov addition reaction. The CH3, CH double bond CH2 in same propene react with hydrogen bromide, HBr. The H plus and Br minus in presence of peroxide, H2SO5, kerosene, peroxide monosulfuric acid, H2S2O8, peroxide disulfuric acid or martial acid, peroxide monophosphoric acid, peroxide diphosphoric acid, chromium pentoxide, barium peroxide, sodium peroxide, hydrogen peroxide. Peroxide compound contain all compounds can be used means this reaction follow the anti-Markovnikov addition reaction against the Markovnikov addition reaction known as anti-Markovnikov addition reaction. What is the meaning of Markovnikov addition reaction? Negative part of the addendum attach itself carbon bearing less number of hydrogen known as a Markovnikov rule, Markovnikov addition reaction. Here by using of peroxide linkage, by using of peroxide compounds, in the negative part of the addendum attach itself carbon heavy highest number of hydrogen. In the negative part here, in the Br minus attack on the CH2 carbon to form of CH3, CH2, CH2, Br. By using of Markovnikov rule, isopropyl bromides are formed. By using of anti-Markovnikov rule, anti-Markovnikov rule, in the anti-Markovnikov rule means to form of N-propyl bromide. By using of Markovnikov rule means isopropyl bromide in same reagent. By using of anti-Markovnikov rule, by use what? Keros acids. Peroxide compounds means to form of N-propyl bromide. It is a anti-Markovnikov addition reactions. Next one, from the alkane. For example, alkane, methane. In the alkane react with the chlorine in presence of sunlight, ultraviolet radiation, UV radiations to form of alkyl halides. In this reaction follow the free radical substitution reaction. Already we have learned free radical substitution reaction by using of sunlight. H nu. H is a Planck constant, mu is a frequency of radiation. In this Planck constant and frequency of radiation combination gives a UV radiation. That UV radiation dissociate halogen into free radical. That free radical substitute in the place of hydrogen in alkane. So, in the, for example, methane react with the chlorine to form of methyl chloride and methylene chloride. In then what? In the chloroform and carbon tetrachloride. So mixture of in the monohalo compounds, dihalo compounds, trihalo compounds, tetrahalo compounds are formed. These compounds can be separated by fractional distillation. Don't forget fractional distillation. For example, methane CH4 is a react with Cl2 in presence of light radiation, UV radiation. In the Cl substitute in the place of hydrogen. So CH3 Cl plus hydrochloric acid is removed. In the CH3Cl further react with the chlorine to form of CH2Cl2. Again, one more of HCl removed. The CH2Cl2 further react with the chlorine to form of in the CHCl3 plus hydrochloric acid removed. The CHCl3 further react with one moles of chlorine to form CCl4 plus hydrochloric acid is removed. Is a methyl chloride, methylene chloride, chloroform, carbon tetrachloride. Methylene chloride, methyl chloride, methylene chloride, chloroform, carbon tetrachloride. Carbon tetrachloride contain totally how many halogen? 4 halogen. So tetrahalo derivative, tetrahalo organic compound, polyhalo organic compounds. In the chloroform contain totally how many collagen? 3 collagens are there. Trihalo organic compounds. Methylene chloride totally contain how many collagen? 2 collagen. Dihalo organic compound. It is a monohalo organic compounds. Monohalo organic compounds. So mixture of monohalo, dihalo, trihalo, tetrahalo organic compounds are formed. These compounds can be separated by using of fractional distillation. These reactions all are follow the or involve the free radical substitution. Don't forget free radical substitution. What is a free radical? The Cl2 and methyl is a free radical. Methyl radical and Cl radical. Already we have learned in last class free radical substitution reaction. So in this reaction all are follow the free radical substitution reaction. Okay. The next one, halogen exchange reaction. Halogen exchange. Exchange of halogen reactions. First one, Finkelstein reaction. Finkelstein reaction. In the Finkelstein reaction, it is used to convert chloro-bromo-alkane to iodoalkane. Chloroalkane to iodoalkane, bromoalkane to iodoalkane. For example, ethyl chloride, CH3, CH2Cl, CH3, CH2Br, ethyl chloride, ethyl bromide, chloroethane, bromoethane. React with sodium iodide, NaI, sodium iodide, NaI. In presence of triacetone as a catalyst, CH3, COCH3, triacetone as a catalyst. Here, in the Cl replaced by iodine, here Br replaced by iodine to form of CH3, CH2I plus NaCl, here CH3, CH2Br plus NaBr, CH3, CH2I, NaCl, CH3, CH2I, NaBr, ethyl iodide. In the ethyl iodide can be prepared from the ethyl chloride and ethyl bromide. So halogen exchange, chlorine halogen, iodine also halogen, bromine halogen, iodine also halogen. So chlorine replaced by iodine or bromine replaced by iodine. Alkyl chloride can be converted to alkyl iodide or alkyl bromide can be converted to alkyl iodide. So halogen exchange reaction, especially iodoalkane can be prepared by Finkelstein reaction. Iodoalkane can be prepared by Finkelstein reaction. Next one, Schwarz reactions. Schwarz reactions. The Schwarz reaction is preparation of alkyl fluoride from the alkyl chloride and alkyl bromide. CH3Cl, CH3CH2Br. They react with the silver bromide, silver fluoride, AgF, or in the stibbium fluoride, SpF3, or arsenic, AsF5, arsenic fluoride, or mercury, Hg2F2 as a catalyst. By using any one catalyst, ethyl chloride or ethyl bromide, chloroalkane, chlorobromoalkane, react with the silver fluoride or stibbium fluoride or arsenic pentafluoride or mercury fluoride, silver fluoride, AgF, silver fluoride, heated in certain temperature, chlorine replaced by fluorine, bromine replaced by fluorine. So CH3, CH2, F plus silver chloride removed. Here CH3, CH2, F plus, then what? Silver bromide. Silver bromide. Chlorine replaced by fluorine, bromine replaced by fluorine. Then chlorine, fluorine, bromines are halogens. This reaction also is an example of exchange of halogen reaction. Especially fluoroalkane can be prepared from Schwarz reaction. Don't forget Schwarz reactions. Next one, Hans-Dicker. Hans-Dicker reaction. In the Hans-Dicker reaction, preparation of especially bromoalkane. In the fatty salt of carboxylic acids of in the silver, Ag, is a react with bromine, Br2 gives. Then monocarboxylic acids of carboxylic acids. Monocarboxylic acids of fatty acids of silver metal. Silver propionate, CH3, CH2, C, totally 3 carbon. 3 carbon means what root word? Propanoic acid. Propanoic acid contains hydrogen replaced by silver metal. So it is a silver propionate. The silver propionate is treated with bromine, Br2. Ethyl chloride, CH3, CH2, what? Br. Ethyl bromide plus carbon dioxide plus silver bromide, AgBr. This method preparation of alkyl bromide. Alkyl bromide can be prepared from Hunt-Sticker reaction. Alkyl fluoride can be prepared from Schwarz reaction. Alkyl iodide can be prepared from Finkelstein reaction. Alkyl chloride can be prepared from free radical substitution reactions. It's an important reaction. It is one of the neat question in 11th standard. Alkyl halide can be then alkyl halide. Then it is called what? Alkyl chloride, alkyl bromide, alkyl fluoride, alkyl iodides are. In the starting material is the synthesis for the many more organic compounds. Here, alkyl chloride can be prepared from the free radical substitution reaction. Alkyl bromide can be prepared from Hunt-Sticker reaction. Alkyl fluoride can be prepared from Schwarz reaction. In the alkyl iodide can be prepared from Finkelstein reactions. Okay. In the next one, physical properties. Physical properties of hollow alkane. In the totally, 4 types of physical properties are there. 4 types of physical properties are there. One is a physical state. Physical state. Another one, boiling point, then melting point. In the next one, solubility, then density. Physical state, boiling point, melting point, solubility, density. What is a physical state? Pure hollow alkanes are colorless. Alkyl bromide and alkyl iodides are colored in nature in presence of light radiation. It is a physical state. In the compound contain 3 carbon. 3 carbon contain compounds are 3 carbon present in a compounds are in the what? Colorless liquid, colorless gas. Above 3 carbon or in the more than 3 carbon contain compounds of alkyl halides are in the what? Liquid or solid. It is a physical state of halogens or alkyl halides, hollow alkanes. Pure hollow alkanes are colorless. Alkyl bromide and alkyl iodides are colored in nature in presence of light radiation. The compound contains 3 carbon of the hollow alkanes are gases, colorless gases. In the more than 3 carbon present in all hollow alkane compounds are then what? Liquid or solids. It is a physical state of what? Hollow alkane. Next one, boiling point and melting point. Boiling point, then melting point. In the boiling point, melting point of hollow alkane is what? Always higher than the hydrocarbon because of intermolecular attractive forces in hollow alkane higher than the hydrocarbon of same number of carbon atom. For example, in the CH3, CH2, CH2Cl compared with the CH3, CH2, CH3. In the N-propyl chloride contain totally how many carbon? 3 carbon. 3 carbon. In the propane contain totally how many carbon? 3 carbon. Then both the compounds have same number of carbon atom, but N-propyl chloride have higher melting and boiling point than the propane in same number of carbon atom because of in N-propyl chloride have intermolecular attractive forces of hollow alkane greater. What is the meaning of intermolecular force of attraction? Van der Waals force of attraction, dipole-dipole interaction. So in the Van der Waals force of attraction, dipole-dipole interaction is known as intermolecular force of attraction. So intermolecular force of attraction of Van der Waals interaction, dipole-dipole interaction higher or greater in hollow alkane than the hydrocarbon. That's why in the boiling point, melting point of hollow alkane greater than the in the what? Hydrocarbons. Next one, boiling point, melting point increases with the increase in mass of the halogen in same number of carbon. Don't forget, boiling point, melting point increases with the increase in mass of halogen in same number of carbon. For example, CH3I methyl iodide is greater than CH3Br is greater than CH3 what? Then Cl is greater than CH3F. Methyl iodide, higher boiling point, melting point, then the methyl bromide, then the methyl chloride, then the methyl fluoride. In the four carbons have same number of carbon, one carbon. But iodine mass higher than the bromine, then the fluorine, then the chlorine, then the fluorine. So mass of the halogen increases. Boiling point, melting point also increases in same number of carbon, one carbon, same number of carbon. Another one, number of halogen increases, boiling point, melting point also increases. For example, carbon tetrachloride CCl4 greater than chloroform CHCl3 greater than CH2Cl2 greater than CH3Cl. It contains total how many halogen? One halogen. That compound contains how many halogen? Two halogen. That compound contains how many halogen? Three halogen. That compound contains how many halogen? Four halogen. So number of halogen increases, boiling point, melting point also increases. So carbon tetrachloride higher boiling point, melting point than chloroform, then methylene chloride, then methyl chloride. The next one, number of carbon increases in same number of halogens, boiling point, melting point increases. For example, N-butyl chloride CH3, CH2, CH2, CH2Cl higher than CH3, CH2, CH2Cl higher than CH3, CH2Cl is higher than CH3Cl. It contains total how many carbon? One carbon. That compound contains how many carbon? Two carbon. That compound contains how many carbon? Three carbon. That compound contains how many carbon? Four carbon. So number of carbon increases, but same number of halogen, one halogen. Same number of halogen, boiling point, melting point also increases. Boiling point, melting point increases. The next one, in isomeric alkyl halide, CH3, CH2, then what? CH2Cl. Another one, CH3, CH2, and then CH, and then CH3, bond Cl. Then CH3, CH3, bond CH3, ing bond Cl. N-butyl chloride, secondary butyl chloride, tertiary butyl chlorides. In the tertiary butyl chloride, higher melting point than N-butyl, then isobutyl, secondary butyl chloride, then the N-butyl chloride. N-butyl chloride, higher boiling point than isobutyl chloride, then tertiary butyl chlorides. So it is a primary alkyl halide. It is a secondary alkyl halide. It is a tertiary alkyl halides. Tertiary alkyl halides. In among the isomeric alkyl halides, the three compounds are same molecular formula. Among the isomeric alkyl halides, in isomeric alkyl halides, boiling point depend upon those molecules occupy the larger surface area. Those molecules occupy the larger surface area means intermolecular force of attraction increases. Intermolecular force of attraction increases. Boiling point also increases. Among the three compounds, N-butyl chloride occupy the large surface area. It is exists in more intermolecular force of attraction. That's why boiling point increases compared to another two compounds. So N-butyl chloride higher boiling point than the secondary butyl secondary butyl chloride higher boiling point than the tertiary butyl chloride. Then melting point. In boiling point, in what? Primary is greater than secondary, greater than tertiary. Melting points depend upon the molecule contain atom or group of elements better packed in nature. Comparing these three compounds in the methyl group, then chlorine atoms. In tertiary butyl chloride, better packed in nature. That means called what? In the tertiary butyl chlorides are spherical shape, spherical shape. That's why melting point higher. So melting point of in the tertiary butyl chloride higher than the secondary butyl chloride higher than the in the primary N-butyl chloride. So melting point tertiary is greater than secondary is greater than primary. So boiling point depend upon those molecules occupy the larger surface area. Because of intermolecular force of attraction increases, boiling point also increases. Melting points depend upon those molecules which contain atom or group of elements present in better packed nature. That means called spherical shape. So spherical nature increases, melting point increases. Occupy the larger surface area increases, boiling point increases. It is order. Next one, solubility. These all alkyl halides are polar covalent bonds, polar covalent compounds. The polar covalent compounds only soluble in organic solvent like benzene, chloroform, carbon tetrachloride, carbon disulfide, acetone, ether, alcohols only, not soluble in water molecules. Because of these molecules all are do not associated with the intermolecular hydrogen bond of water. Water would intermolecular hydrogen bond form agade, other water would soluble agade. Next one, density. The density of all alkyl halides, higher than the hydrocarbon, hydrogen same molecular mass, because of there is no hydrogen bonds. So all alkyl halides of liquid higher density than the hydrocarbon in same number of carbon atom or comparable mass. It is a physical nature, physical property of what? Alkyl halide. Again I will say physical state, polymer melting point, solubility, density. Okay students, today topic over. Next topic we will meet the next video. Thank you.